Thanks for tuning in with us on this little journey. We're four mechanical engineering students at the University of Victoria, and we're here to talk to you today about using wood fiber as a biomaterial for bone implants.
As this is not yet a commercially produced product, only a few groups of scientists have produced these bone implants made from wood. They have been used for experimentation and studies and are therefore used in small quantities. As such, the harvesting method is not representative of what it may be in the future when the wood implants are produced on a larger scale. For one study, a European white birch tree was used, cut from a forest in southwestern Finland. The tree, of course, had been grown naturally. This tree was likely cut by a chainsaw and removed by light-duty truck. Small blocks were then cut from the outer part of the tree, opting to use the live wood rather than the dead heartwood. These blocks were about 30 by 10 by 5 centimeters each. The blocks were then sent to the Helsinki University of Technology for heat treatment. Some blocks were left untreated, some heated at 220, some at 200, and some at 140 for 2 hours each. The heat treatment was done in the presence of water vapor in order to prevent combustion. The wood goes through a series of chemical changes as the temperature and time increase. With all of the treated and untreated samples, they then handcrafted cone-shaped implants using a lathe. These samples were then sterilized by being dipped in 70% ethanol solution and then rinsed with sterile deionized water. This completed the preparation of the samples, and they were then ready for implantation in rabbits. Briefly, I will explain another method here by a team of Italian scientists. Similarly, they started with a block of wood, except from a rattan tree grown in India. They heated the wood until it was pure carbon, and then sprayed it with calcium, creating calcium carbide. The calcium carbide is then converted into carbonated hydroxyapatite, which is then ready for implantation. It will be interesting to see which method is ultimately used when wood bone implants become commercial.
In order to implicate the wood fibers into the bone implants, we must first understand the composition of the bone. This is a quick breakdown of the bone composition in the human body. It is made up of about 30% organic matrix, 90 to 95% being collagens, with 5% being proteins. Next, about 60% is inorganic compounds. These, of course, are the minerals: your calcium, your phosphates, carbonates, sodiums, chlorides, etc. And lastly, about 10% of the bone composition is water. With these properties, the bone is able to fulfill its main purpose, which is to biomechanically adapt to the physical and chemical environments within the human body. Now, there are two types of bone in the human body. There's a lamellar bone, which seen in this picture has perpendicular rows of collagen bundles kind of organized together, and there's the woven bone, which is known as fibrous bone with no organization of collagen bundles. As you can see, it's kind of just separated anywhere. The woven bone is mechanically weak, and having the perpendicular rows of collagen bundles in the lamellar bone makes it pretty strong. So in order to choose a proper wood with these characteristics that'll mimic this microstructure, the proper wood must have the following biomechanical properties. The wood must be non-toxic, biocompatible, have the biochemical strength to withstand forces subjected to the original bone. It must be bioactive. For those of you who don't know what bioactive is, it's when a substance has a positive effect or interaction with the human body that induces localized healing. In this case, it's the wood reacting with the bone fragments already present, and have a composition which allows for bone ingrowth and outgrowth. Essentially, that's just the wood fibers interconnecting and interlacing with the bone that's already present to complete the structure, and have one complete bone that is totally connected with the wood and the already present bone fragments. So studies have shown that the most compatible wood right now for bone implants is the hardwood birch. This is a picture of a bunch of birch trees growing on a lake. It's either autumn or fall. It's just beautiful tree. If you break down the birch, it can be separated into 4 sections. A is the vessel element. It's typically bar-like or scaleiform. B would be your libriform fibers. C would be your tracheids, and D is your horizontally orientated ray peritoneal cells.
Now, to cover how wood used as a biomaterial will impact the environment, we can look into the two main factors, the first being the harvesting of the wood. So used in the previously mentioned study was birch trees, which is a hardwood. It's an already commonly harvested tree. It's found primarily in Europe, used for decorations and furniture. It's also found and harvested in Canada. As you can see by this graphic, the coverage in Alberta of white birch. And also, the same study found that other hardwoods could be feasible for this, so not just limited to birch. So we can take a look at the hardwoods harvested well below the sustainable harvest line shown in this graph, based on a study done by the National Forestry Database for Canada. We can look at the second factor here, which is heat treatment. So the wood is heat treated to alter the chemical composition. It's not a new thing, it's already common, has been done for years, specifically for pallets mainly, and it's an environmentally safe process and does not use any harmful chemicals. So this application of wood for biomaterials would be environmentally safe.
Current materials used for bulk bone replacement and regeneration are complex and expensive. Some techniques require removing bone from another area of the patient, meaning additional surgery. Birch, on the other hand, is an inexpensive natural resource that needs a minimum altering to serve as a biomaterial. Many variables, including the wood moisture content, cost of energy, and temperature, will affect the cost of heat treating these wood implants. Energy cost has been roughly estimated using the draw of a small oven. To operate a small oven at 220 degrees Celsius for 2 hours costs about 28 cents. This size of oven would also be likely able to treat multiple implants at the same time, so cost of energy is negligible. Additional treatments may include the addition of a calcium coating, which after several chemical changes with carbon turns into calcium hydroxyapatite. This structure can now be implanted as an artificial bone. One bone implant using this process costs about $850. On the other hand, the surgery alone to remove bone material from a hip to be used in a bone graft costs $2,000 to $3,000.
Hey everyone, just want to say thanks for tuning in and listening to us talk about using wood as a biomaterial. I hope you enjoyed this video as much as we enjoyed making it for you, and have a wonderful day.